So every once in a while in a physics problem, you'll come across an equation like this that you're expected to solve. The problem is, with an equation like this, where you've got a cosine mixed with a linear function, there is no way on earth that you can solve this thing. We simply don't have the math for it. In fact, you can't solve it algebraically. It's called a transcendental equation. So no amount of algebraic manipulation is going to get you an answer for it. And yet you know that the answer exists because if you graph this function, right, here's x, and here's this equation that we've got here. We'll call this thing f of x. You're looking for where this f of x equals 0. You can graph it and see that there's clearly a root here somewhere between x equals 0 and somewhere and x equals 1. We're going to call that x0 for where x gives you a 0 value for the function. And what we're going to do is we're going to go through a method of how you can use a computer to find where this x0 is. It's going to be called the method of bisection. The way you start the method of bisection is you start with a value of x that you know is to the left of x0. Right? So in this case, that's going to be on the positive side here. Then we're going to pick a value that you know is to the right of x0. And in fact, let's make a bad guess. Let's put this bad guess farther over here. So I'm going to start with a guess that is far to the right here of x0. The better guess you make at the beginning, the quicker this method goes, but I'm exaggerating the badness of the guess here. Since I've got XL and XR, right, I can get those off of the graph, which is an important lesson for this video, is that you always need to graph this function, or these functions, before you start looking for roots, because you need to know where to go looking. I'll show you an example of how that breaks down in the code later on. Once you have this XL and XR picked, you evaluate this function f of x at each of those points. So at XL, that's going to give you the function value on the left, and at XR, down here, that's going to give you the function value on the right. Right? I don't really care which one is above and which one is below, as long as they're on opposite sides. Right? I need one to be above the root, one to be below the root. What that means is one of these is going to be a positive number, one of them is going to be a negative number. Again, it doesn't matter which is which as long as they have opposite signs, right? Because if I picked an x left here and an x right here, I'm never going to find this 0 because the root needs to be in between the two. The next thing that we do is we guess where the root is going to be. The guess we're going to make is the midpoint between x left and x right. So I take these two here. Graphically what I'm doing is I'm going to the midpoint here. So x in the middle. The way our computer code is going to do that is simply going to calculate the average of the two. So we'll have x left plus x right divided by 2. So that's our first guess, right? It's not a very good guess because I've got a pretty big gap there, but it's better than x left or x right. And that's the purpose of the method of bisection, is to get a better guess with each time we go around the method. So what I do here is I've got my function here. I can have my computer code evaluate that. So I can evaluate the function at the midpoint. So now I've got 3 values for the function. I've got the function value on the left, the function value on the right, and the function value in between those two. And the question I need to evaluate next is whether this new point, this new guess, is to the left or the right of the root. Basically, I want to ask, does it have the same sign as x left, or does it have the same sign as x right? It's got to have the same sign as one of them, because unless I've gotten smack dab on the root and gotten a 0, then it's got to have the same sign as one of these two. It's got to be either positive or negative. So we have the computer ask us the question, or ask itself the question, I should say, does f middle have the same sign as, let's say, f left, question mark, right? Because it'll either be f left or f right. An easy way that we can check that is to check for whether f left times f middle is greater than 0, right? Because when two numbers have the same sign, if you multiply them together, you get a positive number, right? Because if it's a positive and a positive, multiply those two together, you get a positive. If it's a negative and a negative, multiply those two together, you get a positive again. On the other hand, if they have opposite signs, if it's a positive and a negative, or a negative and a positive, you'll end up with a negative. So if the answer is yes, yes goes off to the right on flowcharts, doesn't it? Suddenly we're turning this into a flowchart. If the answer is yes, then we know that xm is on the left of the root. If the answer is no, then we know that xm is on the right. Right? So let's check over here. Does fm have the same sign as fl in this example? No, it doesn't. If I were to multiply this number that's a negative times this number that's a positive, I would get out a negative number. So I'd say no, so xm is on the right. And you can tell that graphically, right? That xm is on the right of this root. So here's the important part. Now what I do is I'm going to replace x right with the new xm that I just calculated. Right? So in other words, I'm not going to worry about this x right anymore. I'm going to overwrite that because I know the root is not out here. Right? I know that if this thing is negative and this thing is negative, the root can't be anywhere in between here. If this is positive and this is negative, I know the root has to be in between here. That makes this midpoint my new right point. So where I previously had fr and xr, I can now replace that with the value of xm and fm that I just had. Then we can repeat, right? So we'll take these two, we'll go to the middle, right? Again, we're just calculating the average. So this is my new xm, which makes this point right here my new fm. Then I just repeat over here. Does fm has the same sign as fl? Well, I look up here, this is positive, this is positive. Positive times positive gives me positive. So the answer is yes. That means that xm is on the left. Obviously, you can tell that here. It's to the left of x0. But you notice it's closer than the previous guess was, which is pretty great. So now what I can do, I can replace, instead of replace xr, I can replace xl with xm. So now we'll just get rid of this part over here, and we'll rename this xl and fl. And so I replace whichever one it matched with, right? I've had to change which one I replaced. So here we replace replace xl, had to get my grammar correct there, with xm. Here we replace xr with xm, right? And then I can repeat again, right? I take these two, I go into the middle. This is my new xm. It's closer to this than these were. Actually, it's about the same distance here to xl, so that'll be even better because then on the next one I'll get it right in the middle. I go through the process here. Does it have the same sign as fl? F mid is now right here. No, it does not have the same sign, so it's on the right. Replace xr. Get rid of this xr. Get rid of this xm. This is my new point on the right, my new function value on the right. And now here's the great part. I take these two, I go to the middle, and I'm really, really close to that root. So the question is, how do you know when to stop? Whenever you're close enough to the root, right? So for me right now, close enough is one chalk piece width. So I'm close enough right now. That's going to be called the tolerance value in the code. And basically we're going to keep going until these two end up within tolerance of the actual root, well, within tolerance of each other.
So here's where we define the equation that we're trying to find a root of. So we're looking for this expression to be equal to 0. Here's where we set the tolerance value. So this is how close to 0 we are willing to get, or we are wanting to get, right? So as soon as we're below this, then we know we've found the root. If you want your code to be more accurate, you want this to be a smaller number, but it will take your code more iterations to get through. Down here is where we're going to create our graph, and there's going to be a little bit of animation on the graph to help us visualize this root finding process, which I'll show you in just a second. Then we're going to ask you for two things. The computer is going to ask you for an initial left guess and an initial right guess. And that's going to be based on the graph that it creates, because like we talked about earlier, you always want to make sure that you are graphing before you go root finding so you know what it is you're looking for. So here we're looking for while the x right minus x left is greater than the tolerance value. So this is how close to within each other we want x right and x left to get. Here's where we set up the y values for the x left and the x on the right. Then down here is where we calculate the new middle value. So this is the new value that we are trying to find. And here's that inequality that I showed you earlier, that if the equation's x mid value has the same sign as the left side, then x mid must be on the left side of the root. Otherwise, it's got to be on the right side of the root. So this is just a clever way of finding our way to the root. And we're just going to keep repeating over this whole thing until x right minus x left is greater than the tolerance value, at which point we'll say that we're finished and we'll give the x mid. So let's click on run. All right, so here it's given me my graph to look at. Unfortunately, I can't scroll down because of the dialog box up here. But let's suppose I'm looking for this root over here. I know for a fact that it's 1, but let's pretend I don't know. So let's try a point to the left of 0.5. And then I need a point to the right. So let's make that maybe a 1.5. We'll hit OK. And now what you watch is how it's zooming in. So it's going from on the left and right side, it's getting closer and closer to finding that until finally we end up at 0.992. And we know that that, of course, is 1, right? That's pretty much equal to 1. We can even see on here that I'm getting an intersection of 0 at my value of 1 up here. Let me get this back to full screen. It'll pop it out, but I might as well go back to full screen. All right, so let's try a more interesting equation, because that one we know the answer to. Let's try equation equals, let's try cosine of x minus x. All right, so looking for where x equals the cosine of x. So we'll click on run. All right, so it's looking like it's happening here somewhere around in between 0.5 and 1. So we might as well put those as our guesses. So let's put in 0.5 and 1 as our guesses there. And it's going to keep zooming in on this. Keep trying, keep trying, keep trying. Finally, we get a 0.74 and some change, right? I believe that's the answer I recognize. Let's try the same thing now with cosine squared. So you can try any equation that you want, basically any two functions that you want that you need to find their intersection of. Let's go again with 0.5 and 1. And what you'll notice is it doesn't really matter how close I place that first left and right value, because it's only going to cost me an extra iteration or two, because it's going to get cut in half every single time. Now let's go back to that first example, because I want to show you how we can end up going wrong with this thing. Let's suppose, for example, that I am unaware that there's these two zeros here. Let's pretend I didn't look before I started searching. So let's put in an initial left guess of -1 and an initial right guess of, let's say, 2. Let's see what happens here. Now I've got two roots in between there, and so it's only going to find me one of those. So I am now missing the other root. It seems to have fixated in on the root at x equals 0. I'm never going to find the x equals 1 root that way. So that's why you always want to make sure you graph before you jump into root finding. So anyway, this method of bisection is pretty useful. Next time we will take a look at how we can use some information about the function's derivative to get a little more information and search a little bit more intelligently on this graph.